Welcome back to chapter 18. This will be, I think, our final video in chapter 18, and here we look at problem solving. We'll be solving for both the electric force and for the electric field. Please remember that forces are symbolized by F, and the electric field is symbolized by the letter E, capital E. It is sometimes, in fact, called the E field. So hopefully you'll be able to keep them straight. So let's look at our first example. We want to find the electric force on charge 3 due to charges 1 and 2. So I'm going to have to give you some information. I'll have to give you some sort of a diagram showing the charge distribution. So here we have the picture with the 3 charges in line, 1, 2, and 3. I'll have to give you information about the magnitude of the charges. So charge 1 is a positive 10 microcoulomb charge. Charge 2 is a negative 8 microcoulomb charge. And charge 3 is a negative 15 microcoulomb charge. I'll need to give you some separation distances because we were asking, well, we'll look at that in a minute. So the separation distance between charge 1 and charge 2 is 10 centimeters. Between charge 1 and charge 3 is 50 centimeters. And between 2 and 3 is 40 centimeters. You need to remember that a microcoulomb is 1 times 10 to the minus 6 coulombs. So you can see in the drawing that I, above the charges, wrote their values not in microcoulombs but in coulombs, because in the equation you need to have the numbers in coulombs. So instead of plus 10 microcoulombs, it's plus 10 times 10 to the minus 6 coulombs. And then we have minus 8 times 10 to the minus 6 coulombs for charge 2, and negative 15 times 10 to the minus 6 coulombs for charge 3. Because the question wanted to know about charge 3, I did my distances with respect to charge 3. So between 2 and 3, we know it's 40 centimeters, but we have to have our distance in meters, so 0.4 meters. Between 3 and 1, and again, that's because they ask about the force on charge 3. So between 3 and 1, will be this distance, which is 50 centimeters. So in our diagram, 0.5 meters. We're trying to find F3, so that's the force on charge 3 because of the other 2 charges. And we need to remember, since we're solving for force, F is equal to K, Q1, Q2 over R squared. That's our formula. So we just break it down into parts. We find the individual forces and then add them together and calculate the total force. So step 1, we want to find F31, the force on charge 3 because of charge 1. So we write down the formula. You always start with the formula. F31 is K, Q1, Q3 over R31 squared. Remember that the 3, 1 here, and the 1 and the 3 and the 3, 1 here are all subscripts. They're a little bit below the line. And so we write down the formula and then we plug in our numbers. Notice that when I plug in the numbers, oh, I'm sorry, I overshot again. Notice that when I plug in the numbers, I don't plug in the plus or the minus signs for the charges. We'll talk about why in a minute. So F31 is going to be 9 times 10 to the 9th Newton meter squared per Coulomb squared multiplied by 10 times 10 to the minus 6 coulombs multiplied by 15 times 10 to the minus 6 coulombs. And then that whole product gets divided by 0.5 meters that have been squared. The answer will be 5.4 newtons. If when you do the math, you can't get 5.4 newtons, you need to ask me for help using your calculator. A lot of you still struggle with how to enter these exponents, and a lot of you still struggle when you have an item that's squared in the denominator. So if you're not really good with this, I suggest you do it in parts Take the first number, multiply it by the second, hit enter. Take that new product, multiply it by the third, hit enter. Take that number, divide it by 0.5, hit enter. Take that number, divide it by 0.5, hit enter again. So you have choices. And like I said, I'm more than happy to help you. So make an appointment, or at the beginning of lab or after lab, or usually Wednesdays at class time. I'm always in the classroom. All righty, so what's our answer? 5.4 newtons. Well, how do I know which way it goes? Well, what we're doing is we're talking about what happens to charge 3 because of charge 1. So if you go back to our drawing, what does charge 3 do because charge 1 is there? Charge 3 is negative. Charge 1 is positive. They will attract each other. That means charge 3 would be pulled left because charge 1 is there. So we know F31 points left. Opposites attract. All right, now we need to do the same thing, but what happens to charge 3 because charge 2 is in the picture? So we write down our formula. F32 is equal to K Q2 Q3 divided by R32 squared. Plug in our numbers, 9 times 10 to the 9th Newton meters squared per Coulomb squared, 8 times 10 to the minus 6 coulombs, 15 times 10 to the minus 6 coulombs, divided by 0.4 meters squared. And again, if you don't get the same answer I get, ask for help. So the answer I get is 6.75 newtons, and I know it goes right because charge 3 is negative, charge 2 is negative, charge 3 would be repelled like charges repel, and so that means charge 3 would be pushed to the right. So we're almost finished. What we need to do now is find the total. So to find the total, we have to pick a direction to be positive. I'm going to let to the right be the positive direction. So we know that F3 is F31 plus F32. Well, F31 was 5.4 newtons, but it went left. So I have to write it down as a negative number. That's why there's a minus sign there. F32 goes to the right, so it's a positive. So negative 5.4 plus 6.75 gives us 1.35 newtons because force is measured in newtons. And I know it goes right because my answer was positive. So charge 3 is going to go to the right because of charges 1 and 2. All right, let's look at another example. Oh, I did it again. Sorry. So in our second example, we have the same 3 charges, but now what we want to know is what is F2? What is the force on charge 2 because of charges 1 and 3? So we have our charges, we have our diagram. You'll remember in the diagram that I wrote the charges as coulombs, not microcoulombs, because we need them that way in the equation, and the distance in meters, not centimeters. You'll see I left out a number from my picture. I should have included that R12 is 10 centimeters. I should have, which would be 0.1 meters. I should have put that right here in the picture, and I didn't. You can insert it if you want to, because we need all our distances measured with respect to charge 2. So we're trying to find F2, the force on charge 2 because of charges 1 and 3. So the first step, and we have our formula, we know it's K Q1 Q2 over R squared gives us the force. So our first step, find F21, the force on 2 because of charge 1. So F21 is K Q2 Q1 over R21 squared. Plug in the numbers, 9 times 10 to the 9th Newton meters squared per Coulomb squared, 8 times 10 to the minus 6 coulombs and 10 times 10 to the minus 6 coulombs. Divide that by the distance. Again, this would be 0.1 meters. It has to be squared. Don't lose that little square. All right, it has to be squared. When you do the math, you get 7.2 newtons and it points left. How do I know it points left? Charge 2 is negative, charge 1 is positive. They're going to attract each other. That means charge 2 would be moving towards charge 1, which is left. We need to do the same thing, but we need to look at charge 2 and what happens to it because charge 3 is there. So the formula, F23 is K, Q2, Q3 divided by R23 squared. F23 would be 9 times 10 to the 9th Newton meter squared per Coulomb squared, times 8 times 10 to the minus 6 coulombs, times 15 times 10 to the minus 6 coulombs, divided by 0.4 meters squared. When you do the math, the answer is 6.75 newtons. We know it goes left because charge 2 is negative, charge 3 is negative, charge 2 is going to move away from charge 3, and that means go left. One more step. We need to find F2. So it's the total of F21 and F23. They are both pointing left. I picked right to be positive. So when I plug them into the equation, I have to plug them both in as negative numbers. Negative 7.2 newtons minus 6.75 newtons gives me negative 13.95 newtons, which means 13.95 newtons left. Why left? Because we got a negative answer, and if we say right is positive, that means left is negative. So charge, oh, I'm sorry, that says a 3. My mistake, that should be a 2. So that means charge 2 is going to go left. It's attracted by charge 1 and repelled by charge 3, and that forces it left. All right, for homework, you have a couple of little problems. They'll be in the study guide, but it's just a reminder that these problems go with the previous example. Now, we don't have to have our charges in a straight horizontal line. They could be in a vertical line. I tend to draw them horizontally in the notes so it doesn't take up so much space. They could also be in a triangular configuration. They could be the 3 points on a right triangle. I just opted not to do things that way. All right, let's move along to electric fields. So to calculate the electric field at point A because of charges 1 and 2, you'll notice that our electric field calculations always have a point in space, not a charge that we want to know what's the field at that point. And remember that electric field is E, not F. So we have our distances, we have our drawing, we know how big Q1 and Q2 are. This time they gave it to us in microcoulombs, so again we have to write them in coulombs. If we got lucky and they gave them to us in coulombs, we wouldn't have to do the conversion. We're looking for E, and we know that E is K times Q divided by R squared. So our first step is to find E1. So K Q1 over R1A squared will be 9 times 10 to the 9th Newton meter squared per Coulomb squared times 5 times 10 to the minus 6 coulombs divided by 0.4 meters squared. Because you'll remember if you look back in the picture, even though none of the distances were given as 0.4 meters, if we're measuring from A and we're looking at charge 1, it's 0.2 plus 0.2 to give us 0.4. So that's where our denominator comes from. So 0.4 meters squared, when you do the math, the answer is 2.8125 times 10 to the 5th newtons per Coulomb. How do I know which way it points? Well, we have to go back and look at it. And we have to know, what is charge 1? Charge 1 is a positive charge. At point A, you have your positive test charge. A positive test charge would be repelled by the positive charge at Q1. So positive test charge at A would go to the right because it's being repelled by our positive charge 1. All right, so it goes right. Now we need to find E2, the electric field at A because of charge 2. So we have our formula, KQ over R squared. Plug in the numbers. And then do the math, and you should get 1.125 times 10 to the 6th newtons per Coulomb. And it points left. How do I know that? Well, point A, we pretend we've got a positive charge there. We know charge 2 is negative, so opposites would attract. Our small positive test charge at A would be pulled left towards 2, so the electric field points left. To find step 3, which is our total, we add E1 and E2 together. But first we have to pick a direction. So we said we'll let right be positive. So E1, which went right, got entered as a positive number. E2, which goes left, is entered as a negative number. That's where that minus sign comes from. When we add them together, you'll see we get a negative answer. The minus sign just tells us it points left, so E total is 8.4375 times 10 to the 5th newtons per Coulomb left. Remember that the electric field and the electric force are both vectors, so they have a direction. Your answer is not complete unless you give me a direction. And then you've got a little practice problem, and there's some more in the study guide. This finishes chapter 18. So we will stop sharing and we will stop the recording.